Okay, thank you very much. And I would like to thank the organizers for inviting me here. It's great to be in Latin America for the first time, actually. I'm enjoying the conference so far. I'd like to present some, it's actually work in progress, so it's not really written up, or at least not finalized, but it's work in progress jointly with a group of people, Gianluca Crippa from Basel, Nicolai Gusev from CISA in Trieste, and Stefano Spirito also from Basel. And it's about a seemingly innocent PDE. It's an incompressible continuity equation or a transport equation, which I wrote here. So the transport equation is actually just this one here, and just for simplicity, we always assume incompressibility. Of course, if the data and if the velocity field here is regular enough, then the theory of this equation is very elementary, very simple. But of course, as you know, there's been a lot of stuff going on for the case that the transporting field is of less regularity than, say, Lipschitz. So what I'm going to do is I will give a brief overview, or I will recall for you the main features of the theory of DiPerna-Lions. That was hinted at in yesterday's talk by Vladimir Neves. And then I will show you two results that I obtained jointly with these other guys on renormalization defects, so on the breakdown of the DiPerna-Lions theory, if you like, in case the velocity field is pretty irregular. And we proved that by a convex integration approach that has some or a lot of similarities with the by now well-known approach of Lellis-Székelyhidi for the Euler equations, but also some new features. Well, good. So these are the equations that you all know. There is a scalar density that is being transported by a velocity field v. And I won't bother a lot about specifying the domain. It will be either a domain without physical boundaries or a bounded smooth domain. It's not really relevant for our results. And then in case there are physical boundaries, of course, we set the usual impermeability condition. And we may or may not want to consider the Cauchy problem where only the initial density is prescribed. And then the classical viewpoint on these equations is, of course, that V is a given velocity field, and you want to solve for rho. And in this case, this is a formally well-posed system. Now, just two quick slides on the very classical theory, which is very elementary, as I said. So what you do if everything is smooth, or more precisely, if the initial density is bounded and the velocity is Lipschitz in space, what you'd usually do to solve the PDE is to solve the characteristic ODE. That means you want to solve an ODE where the right-hand side is the velocity field for any initial data. And then it's easy to see that, well, first of all, if V is Lipschitz, then there is a unique solution to that ODE. And then it's easy to see that the unique solution of the continuity equation is given just by pulling back the initial density by the solution of the ODE, by this flow. Now, while this, which is essentially the method of characteristics, while this leads to existence, but also to uniqueness immediately for V Lipschitz, there is another way to see uniqueness. So suppose now that everything is smooth again, one way to show uniqueness, if you don't want to resort to characteristics, is to take the continuity equation, to multiply it by rho, or by 2 rho, and then, well, what you get is this. And by the chain rule, and this is kind of the most delicate step, it's not delicate, of course, in the smooth setting, but it turns out to be crucial. By an application of the chain rule, you find that not only is rho a solution to the continuity equation, but so is rho squared. And in fact, any function of rho would be another solution to the continuity equation. And then, of course, you can integrate, and the divergence term will vanish in the integral by virtue of the boundary condition on V, and you will get this here. You will get the conservation of rho squared, which means, of course, if you started with 0, then you'll be 0 for all times, and then by linearity, you get the uniqueness. Okay, now that's not a big deal. What is, of course, much more difficult is what happens if the transporting field is not Lipschitz, which means that you cannot apply the Cauchy-Lipschitz theorem for the associated ODE. So first of all, if things are irregular, as usual, we'll have to find a weak formulation, and that's not a great surprise. Of course, you multiply by a smooth test function and integrate by parts, etc., and you get this here. If you choose to include initial data, then you get this this integral for the initial data. But maybe one thing to notice for later reference is that the definition of the weak solution makes sense as long as rho and V are in conjugate LP spaces. Good. Now, the problem is, and that's why I emphasized the use of the chain rule in that easy calculation on the second slide. We want to use, if we want to prove uniqueness without resorting to characteristics, to the associated ODE, then we need to use the chain rule. Now, if V is not regular, we cannot use the chain rule. And so the idea of DiPerna-Lions was to define a notion of weak solution that postulates the chain rule. And this results in the definition of a renormalized solution. So you have a bounded weak solution, and it's called renormalized if what we found out by using the chain rule just happens to be true, although you possibly don't have enough regularity to use the chain rule. So it means if I take just any function of rho, say a C1 function, any function of rho, then that function of rho will still be a solution of the continuity equation. Now, maybe one remark is in order here. As I said, the classical approach to a continuity equation is to look at the associated ODE. What DiPerna-Lions did is to do it the other way around. So one of their main motivations, at least that's what they say in their introduction, to study this theory or to develop this theory is to study ODEs when the right-hand side is not Lipschitz, but only Sobolev. So they study the ODE by going back to the continuity equation, to the PDE, and they do all this theory for the PDE, and then they get nice results for the ODE. So it's kind of the other way around than the classical approach. And then I try to assemble the main features of the DiPerna-Lions theory, but I have to disclaim that what they do in their paper holds in much larger generality. So first of all, if omega is unbounded, you can replace all the Sobolev and LP spaces by their local versions, okay? But more importantly, everything still holds true if the divergence of V is not necessarily 0, but only bounded. And you may want to impose some growth conditions, things like this. But okay, let's look at the simplest situation. Now, it's crucial in the DiPerna-Lions theory that you have a Sobolev regularity, at least a Sobolev regularity in space. So we suppose that our velocity is in W11, and that the Sobolev norm is integrable in time. And then the initial density should be bounded, and then we have the following assertions. So first of all, we have existence and uniqueness of renormalized solutions. Now, the uniqueness basically follows from the definition, that's the reason they defined the renormalized solutions they did the way they did, to get the uniqueness of the renormalized solution. The existence, of course, is more difficult, and so is the following statement that kind of justifies the whole theory. So it's not that renormalization is a kind of singling out criterion. It's not like an entropy criterion where you have a bunch of solutions, but the renormalized one would be the correct one or the physical one. But it can actually be shown that under the given assumptions, when you have a bounded weak solution, it must be renormalized and therefore unique. And then, as I said, the main motivation for studying renormalized solutions is to get back to the ODE again. The statement is, under the given assumptions, you do have a solution of the ODE, you do have an associated flow for the PDE, at least for almost every initial data here. Okay, and then of course you can give an explicit characterization of the renormalized solution as the pullback of the initial density by that flow. Good. Now, what Vladimir said in yesterday's talk also was that the crucial tool to establish the existence of the renormalized solution is the commutator estimate. So, of course, what you do is you mollify the initial density, and then you get, then of course the classical theory applies, and you get a solution for every mollification parameter epsilon, and then you want to let that tend to 0 and so on. And it turns out you want to study the commutator of the divergence term. And so, I mean, you can take the entire divergence term and mollify that, or you could mollify the density and then take the divergence. It turns out that with the Sobolev regularity, you can prove that this is small in a suitable norm, and you can pass to limit. And another important remark is that the Sobolev regularity can be weakened to BV, and that's the content of an important paper by Ambrosio, 2004. Okay, now the theory is sharp in various senses, which are given by the three classes of counterexamples that I'd like to shortly discuss here. So in the original paper, there is already a counterexample when you have almost one derivative, so you're in WS1 for all s less than 1. So you have almost one weak derivative, but not quite. And it turns out that this is not enough to ensure renormalization. So this means when you only have this regularity, you can construct, you can construct a field with only that regularity for which you get non-unique renormalized solutions. At least when the initial data is not identically 0, you get several renormalized solutions. Only if the initial data is trivial, then every renormalized solution has to be trivial itself. Second class of counterexample, it's usually attributed to Depauw, who wrote a nice short compte-rendu note about it. That is very nice and easy to read. But it goes back to a previous construction by Eisenmann that's actually much older than the DiPerna-Lions theory. Independently, at the same time, Colombini, Luo, and Rauch had constructed a very similar counterexample. But I'm stating the version of Depauw, who proved the following. You can have a velocity field in L1 loc in time and BV in space. Now, L1 in time and BV in space is, by Ambrosio's result, is enough to make the renormalization theory work. But the crucial thing is not this loc, but it's this loc. So at time 0, you have a singularity, which means that you can't integrate the BV norm up to time 0. And this defect suffices to get a counterexample to renormalization. So again, you get, okay, this is a bit different than the first example. So in this example, you can get a non-trivial weak solution for the continuity equation starting from trivial initial data. And of course, that solution can then not be renormalized. And as a last counterexample, I would like to mention the results of Alberti, Bianchini, and Crippa. So that's a series of 3 long papers or 2 long papers. But as a corollary of the studies, an intricate study of the geometric measure theory properties of velocity fields, and they can construct a Hölder continuous field that's Hölder continuous for any exponent less than 1, where renormalization still fails. Okay. So you have here almost one derivative in the Sobolev sense, you have here almost one derivative in the Hölder sense, but in both cases you cannot guarantee renormalization.
What kind of solution?
Bounded.
Or
Weak. Yeah, so that's not renormalized. Yeah. It's a bounded weak solution. Now, the main objective of the project I'm presenting here is to quantify this kind of breakdown of the renormalization theory. And we use the notion of renormalization defect. It probably has been used previously, but I'm not aware of any work where it's precisely defined. So let's just make the following definition. Certainly, the definition of renormalization tells us that this quantity here, so any function composed with the density, which is a solution of a continuity equation, that should be 0. And if it's not, then it's not renormalized. So the right-hand side is simply called the renormalization defect of that density with respect to the given velocity, and it also depends, of course, on what function beta you choose. Just let me point out that the only function you would need in practice, as far as I'm aware, is the square function. So it's maybe not so important to talk about general beta. Anyway, that could be just a measure or a distribution. It was unknown if it could be absolutely continuous, so if f could be some LP function, whatever. And that's one thing we construct. So for Depauw's counterexample, of course, since if you remember Depauw's example, you had a velocity field that is BV for all positive times, which means that for positive times it must be renormalized by Ambrosius theory, but the breakdown happens at 0. So then your right-hand side here would be Lebesgue in space, but Dirac in time. And so our first result is a generalization of Depauw's example in a certain sense. So we have some technical assumption on beta. It should be even and bijective. At the end of the talk, if I have time, I can explain to you why we need this assumption. But the important thing is we can prescribe any renormalization defect in, say, L1. We can do a bit more than L1. We can do bounded atomic measure. I'm not sure if we can do the singular measure with a singular part, but that's in progress. But let's say F is a diffuse in L1 renormalization defect, and then we can construct a velocity field and a density, both of which are bounded, such that we achieve precisely this renormalization defect. The important thing to notice here is that it's only allowed to depend on T. So, and that comes from the method we use for this theorem. And 2 slides later, I will show you another theorem that is more flexible in the defect. But for this, we simply follow Lellis-Székelyhidi plus a small trick at the end to achieve the renormalization defect. But the trick is kind of not robust enough to allow for anything more than a renormalization defect that's only time dependent. Okay, let me put a few remarks. First of all, well, I mean, the assumption was that F is L1, but we can also do, as I said, say a Dirac measure. So if F is a Dirac measure in time, we get the same phenomenon as for Depauw. Although I have to say, what we construct is not as good as Depauw in this case because he got BV everywhere else and we don't get BV regularity. But we get the same renormalization defect. But if any one of you knows an example of a diffuse renormalization defect, please let me know. But my collaborators and I are not aware of any previous example where we get an L1 renormalization defect. And as I said, the result is kind of limited to a defect that's purely time dependent. And so that's why we were interested in getting this other theorem. Now, we have slightly different conditions on beta, and again, if I should have enough time in the end, I can indicate why we need this strong convexity. Strong convexity means that, well, if beta has two derivatives, it means the second derivative is bounded from below, bounded away from zero. Okay. And now we have also a slightly different assumption on, okay, first of all, this is a result for the stationary equations. That means we have the continuity equation without a time derivative. And previously, we had a result for dimensions 2 and higher. Now we have to take at least 3. So we're looking at the 3D case. Of course, you can do 4D and higher. But we cannot do 2D. And first of all, our method breaks down for 2D. But secondly, more importantly, there are results which tell us it can't work for 2D. Anyway, we get, again, a bounded pair of velocity and density such that we have the stationary continuity equation, and we have a renormalization defect that can be any LP function on the domain. But now P is supposed to be greater than 3. This is because, in the proof at some point we will invert the divergence operator, and if P is greater than 3, we can get a solution from that to that divergence equation that is continuous. And we need that for our convex integration scheme to work. Anyway, so these are two kind of complementary results. We have a time-dependent situation, but the defect is only allowed to depend on time. And we have a stationary situation where the defect depends on space, obviously. And for d equals 2, as I said, this is ruled out by work in progress, again, by Bianchini and Gusev. Actually, I don't know what their paper says because there is no paper yet, but Nikolai Gusev told me that, okay, they prove something like every stationary solution in 2D is automatically renormalized even without Sobolev regularity or BV regularity. Now, oh yes, one remark is, since this is a fluids conference, you would usually imagine the density rho to be a density, which means that it should be strictly positive. And of course, you can trivially achieve that from a bounded density by just adding a constant. Well, and both results use convex integration techniques, although in a very different way. But that gives me the opportunity to show you a bit of convex integration on the next few slides. So in a sense, this is the second part of the talk, is to give you a brief overview and a short explanation of what convex integration is. I know that many of you have actually contributed to convex integration for fluid equations, and I'd like to cite a few people. So, of course, the starting point was the work of Lellis-Székelyhidi for incompressible Euler, and then several people, some of whom are in the audience, contributed to that theory. In particular, there has more recently been the study of solutions of Euler at higher regularity, at Hölder regularity. So those would be results of Tristan and Phil Isa at Rio de Janeiro. But also you can do a lot of other stuff with it. So you can consider incompressible porous medium equations. That's Diego Cordoba, who's in the audience, and Farako Gancedo, and Laszlo has another paper on that. And Roman Schmidtgoy has active scalar equations. You can do compressible Euler, some compressible models. There's a whole bunch of people working on that very, very recently, very actively. And then there is a special case of magnetohydrodynamics by Anne and Helena and Milton. So it's not the full MHD system, but if you look at a symmetric version of these equations, you get the incompressible Euler equations with a passive tracer. And in particular, the passive tracer equation, I mean, that is a continuity equation, which means that actually both the results of Diego and Farako Gancedo and the results of Anne and Milton and Helena already yield non-renormalized solutions of continuity equations. So I'm not claiming we're the first ones to use convex integration to do that. What is novel about our results is that we can exactly prescribe and control the renormalization defect, which was not the main focus of attention in these works. Now, let's get very basic. Let me show you the simplest possible example that I know of a convex integration argument. It's by now, I think it's well known, but it's not attributed to any particular person. I think it was an anonymous referee to a paper of Laszlo and Camillo who suggested this example. So maybe that person is in the audience, but we don't know. Okay. Anyway, so it's a very, very simple problem that we're considering here. We want to, it's all one-dimensional. We want to construct a map from a real interval to the real numbers whose absolute value is 1 almost everywhere. Now, of course, it's not difficult to come up with such a map. The point is rather to illustrate the method by which you can do that with a convex integration type argument. So first of all, we have the concept of relaxed solution. In this case, it means we start with something whose absolute value is strictly below 1. And we start an iteration scheme. So if we're below that absolute value of 1, we keep adding perturbations. So the next step will be the previous step plus a perturbation. And the perturbation is constructed in such a way, first of all, that you will always keep this property throughout the entire iteration process. You will never exceed 1. But secondly, you oscillate at a high frequency, lambda k, which is yet to be determined. And an important feature is that each frequency is much, much higher than the previous frequency. So you have a hierarchy of well-separated frequencies of your perturbations. And then, as I said, you retain this property after every iteration step. You're still a relaxed solution or a subsolution. And in the next step, you want to measure the error. So how far are you still away from being a solution to your problem? So in this case, an obvious error functional would be 1 minus u squared. If you have a solution to u equals 1, this will be 0. Otherwise, it will be strictly positive. Okay. And then, of course, you want to check what happens after every iteration step with your error functional. It should definitely converge to 0 in whatever space. So here it's just in, say, L2. And you can, of course, you can do that computation explicitly. You get that the k plus first error is the previous error. Then you get 2 terms. Okay, let's talk about the last one first, because you see why you need the high frequency. You have here uk times 1 minus uk squared, whatever, something that depends on uk, plus this sine term, and you're still free to choose the kth frequency. And of course, if you choose that large enough, you can make that arbitrarily small. But you have to choose it large enough in comparison with uk, which means that the scale on which the k plus first perturbation oscillates must be much higher than the scale of UK. Okay, so you can then safely ignore this term. And this one, well, again, you need the high frequency to ensure a weak convergence. And in the end, you end up with an error that is strictly smaller than the previous one, measured in terms of the previous one, but you can easily see that you get the error functionals converging to 0. Great. And then, of course, you can also show that your UK is Cauchy in L2, so it converges strongly, and so you can pass to the limit in the error functional, you get I of u is 0, so that limit will be a solution to your problem. Great. So let's get a bit more, let's observe something. I like this example because it displays a lot of characteristic behavior of convex integration type arguments in such a simple situation. Idris, please. Yes.
I'd like to point to this very beautiful, very inspiring. It would be interesting if one can, of course you chose this oscillation, if one can choose different functions, whatever, to accelerate the error to go even faster to 0.
I see. Like to not...
Like in numerical methods, you can have certain determinant procedure.
Right.
But when you move to Newton method, it makes it even quadratic, whatever.
Okay.
Because here you see it's going like basically, somehow it's like it could improve by yk I squared.
Yeah.
So if it's a small, then you cut a little bit instead of like
Right.
just,
Right. I guess in a sense this was what gave the breakthrough for more regular solutions of Euler, that you didn't use a certain kind of perturbation but another one, the Beltrami flows. I think that goes in the direction of your remark. Yeah. So first observation we can make is we can get an exact solution from a relaxed solution. And I'll make clear on the next slide what a relaxed solution will be generally. Then another thing to observe is that you need sufficiently low regularity. So if for the toy example you wanted a continuous solution, well, the only continuous solutions of the problem are constant functions plus 1 or minus 1. And it's certainly not what you get when you use the convex iteration scheme. So you always have a certain degree of irregularity, and it's a very subtle issue, which is not the objective of this talk, to get the optimal regularity. For Euler, that would be the Onsager's conjecture. And then, as we have seen, the construction is always an iteration process that involves perturbations whose frequencies are at a much higher scale after every step. And all this is typical of convex integration. Let me put this in a more general framework. So suppose you have a closed set which is allowed to depend on the domain, and you want to solve problems like u of x. Now, of course, u could be a vector-valued map. U of x is in that set almost everywhere. In the toy example, that's the remark here. In the toy example, your set would be just minus 1 and 1, but you can, of course, come up with more complicated stuff. And then what we didn't see in the toy example, but what is usually of the greatest importance, is that you have a differential constraint. And it will always be a linear differential constraint because you want to add perturbations. You want to have a superposition mechanism, which means you need to have a linear condition. So you have a linear differential operator. A could be something like curl. Curl u is 0 means you're looking for a gradient in kx. That would be a classical differential inclusion. Let me say that this doesn't come from PDEs of mathematical physics, but it rather comes from calculus of variations, where you would like to solve differential inclusions of the form gradient u is in some fixed set. And let me give you an example. For Euler, for instance, that's Camilo and Laszlo's original approach. They write the Euler equations in what they call the Tatar framework, which is essentially what I showed you. So you take the Euler equations, which we all know, and you replace the nonlinearity by a new variable. This makes the system linear. It makes it highly underdetermined, of course. And you couple that with the requirement, well, that the new variable that you introduced should be equal to the nonlinearity. So it's trivial to see that if you have a solution of this, which obeys, in addition, this, then you have a weak solution to the Euler equations. And the way I wrote it here, I was too lazy to write a proper definition of K. The way I wrote it, it seems to be independent of X and T, but really it is once you want to prescribe a kinetic energy density. Then you would, in addition, require that V squared attains some value that could vary with X and T, and then this set here would depend on X and T. Now, of course, there is more to convex integration than just writing a PDE in Tata's framework, but there is a lot of analytical and geometric issues. But most importantly, what you have to ensure is that this constraint set K be compatible with the differential operator A in a suitable sense. So in what you could call classical convex integration, your perturbations would be plane wave solutions. Okay, and the question is, are there plane wave solutions to this differential constraint, and are there enough, and are they compatible with K? So what you want is that the convex hull of K, but now it's not the classical convex hull, it's a convex hull related to the differential constraint. So what's called the lambda convex hull of K should be sufficiently large to allow for enough perturbations you can make. Well, let's talk about what I actually want to talk about the results with Gianluca and the other guys. Recall what was our first theorem. So if we have a renormalization defect that depends on T, then we can find a solution of the continuity equation that has this renormalization defect. So what's the framework? How do we write that? First of all, well, I have to say this theorem comes pretty much straightforward from the techniques of Laszlo and Camillo. It's nothing very original as far as the convex integration side is concerned. It's only that we use a kind of clever definition of the constraint set, which will automatically give us the renormalization defect. So the point in this result is that we don't even bother about this equation for the moment, but we first only look at the divergence condition on the velocity and the continuity equation. And then we do it like Laszlo and Camillo, and here where there would be a rho times V in the original equation, we just replace that by a new variable, which in turn should be the same as the original nonlinearity. I mean, a continuity equation is linear if you fix V, but it's nonlinear in rho and V, if you want to take that viewpoint. So you want this new variable to be the same as the old nonlinearity. And then I have two other conditions that will give me back the renormalization defect. So first of all, we require that the velocity have modulus 1, essentially. So that's the characteristic function of the set where this function g is positive. G is the modulus of the density. And what is G? Well, G is something that depends on F. And it is defined in such a way that, well, first of all, what's inside the beta to the minus 1 is positive. It was one of the assumptions on beta that it be bijective for all positive numbers. So this is positive, so it's bijective. We can invert it, and we get back something that's non-negative. And it will turn out in the next slide why we define it this way and why it's advantageous to consider this constrained set. So, first of all, in the convex integration scheme, we don't worry about the renormalization defect. We just worry about, well, this problem with this constraint set, and then it's pretty straightforward from the usual, by now, usual techniques that you can find a solution to that differential inclusion. But then we can look at our solutions that we get, and we can try to compute the renormalization defect. So we write here the definition of the renormalization defect. We use that beta is even. That was just an assumption, so beta only depends on the absolute value of rho. And then we use that the rho that we got has a modulus that is only time dependent, which means, first of all, that this thing here has no x dependence, so it's simply divergence of v, which is 0. So that term drops out. And for this one, we get, well, the time derivative of beta of g of t. And then g was defined exactly in the way such that this turns out to be f. There's a kind of cheap trick to use the standard, by now standard convex integration techniques to get that defect. Now, what's a bit less cheap is the stationary theorem that I showed you. So let's recall what it said. And that works in 3 or higher dimensions only, and we have a defect. We want to find a stationary solution with a prescribed defect. Now, if we want f to depend on x, on the space variable, I'm not aware of any kind of clever definition of the constraint set that would easily give us that defect. So what we do is we involve the renormalization equation in the convex integration scheme from the beginning. And that has several consequences. First of all, we move away from the Lellis-Székelyhidi theory a bit, because we have now a different kind of differential constraint. We have a different kind of nonlinear constraint. First of all, we introduce variables Vm and W. V is just V. And M should be the momentum. M should be rho times V. And then W should be beta of rho times V. So if you make these substitutions in here, you will find exactly the 3 conditions that we have: the continuity equation, the incompressibility, and the renormalization. Now we have a 0 here. We want to get an f in the third component. The thing is that we will start our iteration process with something that satisfies this inhomogeneous condition, and the perturbations will have 0 here. So we just use a non-homogeneous superposition. That's not a big deal. Great. So that's what I said. First of all, you start with a relaxed solution, which is 0 and 0 in the first 2 components, but the W naught, which that's the component that corresponds to the defect, that will be a solution to the divergence equation for that particular defect that we want to prescribe. And then for all the perturbations we add, we can have the divergence 0 by linearity. Well, and then, okay, I'm almost running out of time. But I said if you want to do a convex integration, you have to study very carefully the geometry of the constraint set and how it interacts with the differential constraint and with the wave cone. Now, the wave cone, that is the set of directions in which you can have oscillatory perturbations that are consistent with the differential constraint. The wave cone consists of all matrices with determinant 0. Because you can view MVW, it's a triplet of 3 vectors. Of course, you can view them as a matrix. And if that matrix is singular, then you can oscillate in that direction. That's a simple calculation, which means you always have this rank 2 condition. If you're in 3 dimensions, you have a rank 2 condition, which means whatever you do, you have to do it along rank 2 connections. And then you have to study the rank 2 convex hull of the constraint set, and it turns out you can do that. Just as a remark, in 2 dimensions, the rank 2 condition would turn into a rank 1 condition, which is much more restrictive, and we can't do the construction we do. Okay. Right, so I don't have more time to tell you anything about this geometric study of the convex hull and how we can represent, in fact, every matrix as a rank 2 convex combination of matrices in the constraint set, but you can somehow do that, and at some point you will get this condition of strict convexity on beta. Good. So let me close with just open problems. So since it's still work in progress, there's a lot still to be done. And for the first two items, I'm not claiming that they are particularly difficult. I could imagine you can easily do them, just we haven't had time to look at them. So the first pretty obvious question is, we have this kind of dual theorems. One of them is for time-dependent equations with a renormalization defect that only depends on time. The other one is for a stationary case. So can we do the non-stationary case? Can we somehow refine our methods to get to the non-stationary case with a renormalization defect that is allowed to depend on both variables? Of course, higher regularity is always an issue. And there is this example of Alberti-Bianchini-Crippa for non-renormalized solutions with Hölder regularity. So I'm pretty optimistic that you could somehow get Hölder adapting techniques from the Euler equations. Sobolev regularity might be more difficult because, in fact, and that's something I wish to close with, if you recall that the definition of weak solution makes sense if V and rho are in conjugate LP spaces, okay? But the DiPerna-Lions theory requires that V be in a Sobolev space with the conjugate exponent. So there is some, and because the Sobolev space embeds into some better LP space, there is some room which makes it conceivable, at least, that you can have a Sobolev field and a density which is not bounded, but which is in some LP, such that rho is not renormalized. That, I mean, I don't know why that would not be possible to happen, although I don't know if it can happen. But I think this is very difficult. In any case, I'd like to thank you for your attention.